We all know the world today is facing a food crisis that is expected to aggravate by 2050. By this year, the world population is expected to grow to 9.7 billion people, and the food demand is expected to increase by 70 to 100% quarterly. Unfortunately, the food production rate is not increasing at the same pace. So why? Why aren't we able to manufacture as much food as we need, and why is it costing so much? And to answer these questions, we should look at the challenges the agriculture industry is facing today. 40% of the crops are lost due to pests, diseases, insects, weeds, while 99.9% of the products that are administered to the crops are lost in the environment, leading to low yield and negative consequences to the environment. So what can we do? How can we improve and help tackle these challenges? One way is to increase the efficiency of the existing pesticides and herbicides. By doing so, we will be able to increase the yield, lower the food costs, and minimize the pollution to the environment. And to do so, one way is to increase the uptake of the existing agrochemicals, and similarly to what is going on with the drug delivery revolution. Okay, and another way to do so is to develop innovative and smart solutions for weed pest control. This topic I will revert back to by the end of my presentation. Many of the products used today in the market are emulsion-based, because a lot of the other chemicals have low solubility in water. We chose to improve these products by focusing on Pickering emulsions. So what are Pickering emulsions? These emulsions are stabilized by solid particles rather than surfactants that accumulate in the interface between the two immiscible liquids, creating a mechanical barrier against fluorescence, which later on leads to phase separation. We chose Pickering rather than the classical emulsions with the surfactants because it leads to a much more stable emulsion that will increase the shelf life, and it has no surfactant, leading to low toxicity. It has been shown that many types of particles can act as stabilizers, but we all know that there's an increase in interest to developing sustainable materials with low environmental footprint. An example for such a material is called shellac. Shellac is a natural resin that has many advantages. It's antimicrobial, it's biodegradable, it's non-toxic. The main component of the resin is a complex mixture of the polyesters and single esters, and the building blocks are uric acids and terpenic acids. But the main drawback of shellac is that it self-polymerizes with time, which impacts the mechanical properties of the material. It has been shown in our lab previously that modifying the shellac with the Jeffamines can actually prevent the self-polymerization phenomenon. Jeffamines are ready-to-use polyethers with primary amino groups at the end of the chain. We chose to focus on two types of Jeffamines: short, 600 Dalton long monoamine, and a longer 2000 Dalton long diamine. The amine groups on the backbone of the Jeffamines undergo a condensation reaction with the carboxyl groups on the backbone of the shellac, and creating a bond. So this leads me to our research objective, which was to investigate the potential of shellac-based nanoparticles to act as a stabilizer for Pickering emulsions that will later on be a platform for agricultural applications. So the first step was to create shellac nanoparticles. As there are very few indications to preparing such nanoparticles, we were very happy to create this material in a very, very effective manner. It's called an anti-solvent precipitation method, as shellac is insoluble in water. We took shellac or modified shellac and ethanol, added it dropwise to a constantly stirring water. The droplet decreased in size, the ethanol dissolved and eventually evaporated, leaving us with a shellac nanoparticle dispersion. We obtained 3 types of shellac nanoparticles. Pristine, the modified shellac with the shorter Jeffamine and the longer Jeffamine. We characterize these nanoparticles using a light scattering and Technion imaging. All the nanoparticles were spherical, ranging between 90 to 200 nanometers. They were all exhibited low polydispersity and were stable for months. The next step was to prepare an emulsion. We chose to work with IPM, isopropyl step, which is a biocompatible oil. And by using high shear homogenization, we were able to obtain a stable emulsion. It should be noted that emulsions that were stabilized by pristine shellac did not result in stable emulsion. So we moved forward with our 2 types of shellac nanoparticles that were modified. We made sure that the homogenization did not significantly impact the size of the nanoparticles before we moved on with our investigation. Okay, so before I share with you the results of our research, I want to show you typical images of our emulsion. You can see here on the left, it may seem that we have 2 layers of our emulsion, but actually it's a very known phenomenon in the emulsion world. It's called creaming. It is a result of the difference between the density difference between the water and the oil. But in fact, we do not have any oil at the top of our emulsions. An emulsion is considered stable as long as coalescence does not occur, as long as we don't have any oil on the top, meaning that these emulsions are stable. We can see here an unstable emulsion where we do have an oil phase on the top. Okay, these are not homogeneously homogeneous in appearance, but if we shake these emulsions, the oil droplets redisperse and we have a homogeneous emulsion. This shaking will not help this emulsion to be homogeneous again. And if we zoom in into our cream layer using an optical microscope, we indeed see many oil droplets, and it is still a stable emulsion with no phase separation. So we started a systematic study with our first type of nanoparticles, the shorter Jeffamine precipitation, constant nanoparticle concentration with varying oil concentrations. You can see here that all the emulsions, we monitored them with time. All the emulsions exhibited a cream layer that was proportional to the oil content, and above 50% oil, we did see an oil layer on the top. So up to 30% oil, we obtained stable emulsions for 5 months. This is a very long period for emulsions. Our mayonnaise usually breaks after 2 weeks or 1 week in ambient conditions. Okay, we continued our research with the longer Jeffamine, and here again we see a cream layer that was proportional to the oil amount, and up to 40% oil. There was no oil phase separation for 5 months. When looking at the oil droplet size, as expected, we can see that the oil droplet increases significantly with the increase of oil content. So we wanted to further investigate our emulsions and to confirm the assumptions that indeed the nanoparticles reside in the interface between the 2 invisible liquids. So we took our emulsion with the long Jeffamine modification to cryo SCM imaging. And we were very, very happy to see these images. You can see here on the right, and the cream layer we can see here the oil droplets. Some are whole, some are broken. The nanoparticles wrapping these oil droplets. And if we zoom in to one of the oil droplets on the left, we can see a beautiful representation of our system. We can see that there are no nanoparticles within the oil. There is a beautiful layer of nanoparticles surrounding oil droplets and still nanoparticles in the continuous phase. This is an emulsion with 10% oil. When we look at the 40% oil, the same nanoparticle type, we again see many oil droplets. These are bigger oil droplets corresponding with our results with the mastersizer. And zooming in, we can see the nanoparticle layer here. The nanoparticles are less dense, which is as expected when we increase the amount of oil, but we leave the nanoparticle concentration the same. So this is still a work in progress. And we saw that it takes months for an emulsion to phase separate. So we wanted to further investigate our emulsion using accelerated stability conditions. So we took using a centrifuge. So we took our two types of emulsions, and the results are very similar to what we've seen in the ambient conditions. On the right, the emulsion 30 minutes under 10,000 G with the shorter Jeffamine phase separated, while our emulsions here after 30 minutes under 10,000 G with the longer Jeffamine modification exhibited no phase separation. So the emulsion, this type of emulsion that exhibited superior stability was our platform for further investigation for agriculture applications. So as I said earlier, there is a growing interest to developing not only delivery systems for agrochemicals, but developing smart solutions for the agriculture industry. An example for such a solution is called robotic weed removal. This application is based on a robot that knows how to differentiate and recognize weeds from crops to eliminate them based on imaging. And the recognition challenge is actually illustrated here in the picture here. This is a picture of a crop, corn crop field with weed that grew in between the lines. Very dense, all are green, and it is very, very challenging to differentiate between the two types of plants, right? So the majority of the weed management that is done today is manually based, okay, leading to an increasing cost. And the robots that existed in the market are inaccurate. Okay, 50% accuracy is not enough, right? And it is crop and plant specific. To improve this type of technique, we should improve the recognition technique by using crop signaling. So what is crop signaling? It's a new technology for visualization of crop and plants using external markers for automated recognition. Okay, here's an example for this technology. In this study, by applying luminescent paint on Roman lettuce, you can see here on the left. This is how it looks. It's kind of hard to see, but you see the dots, okay, under UV exudation. And on the right, we can see here how the program was able to differentiate between the lettuce in red and the weed that needs to be eliminated in green. In a collaboration with Dr. Arnaki from the Technion Institute in Israel as well, we are developing a crop signaling marker based on our newly developed emulsion. The aim of our study is to develop a sustainable marker that has a wide range of recognition. Here, we took our emulsion with 10 and 40% oil with two types of eatable dyes. After shaking them, we sprayed them on cabbage leaves okay, cabbage plants. And by using a hyperspectral camera with 204 bands between 400 and 1000 nanometers, we imaged these plants. Afterwards, we collected a spectral signature. And for further investigation, we performed the data analysis. Okay, so let's look at our data analysis of our preliminary experiments. Our goal is to find a specific index that shows us the difference between the control untreated plant with no emulsion applied to it and the treated plants. Okay? We can see here by using a very, very basic vegetation index called NDVI that after 10 days, okay, after 10 days of constant irrigation in the greenhouse, when we sprayed our emulsions, there's constant irrigation of water, which is even more harsh than what is going on in the field. Okay, we can see that after 10 days, there's still a difference in this index between the control and all of our treatments, meaning that the emulsion was able to adhere to the leaves and not be washed off. Okay, so this takes into account two bands, the NDVI, if we work. Another way to analyze the data is based on SVM, which takes into account the 204 bands and not only the 2 bands that we took in the NDVI index. And this is very, very, very preliminary, just before I got on the plane. We can see that there is a difference between the control untreated plant and the treated plants. Another important aspect when we're talking about agricultural applications is the safety assessment. We looked at our plants a month after treatment, and we can see that all the plants are very much alive, so it's good. But we need to analyze as well statistically to see what we have. So if we look at the biomass change, we see that there is no significant change in the biomass with the 10% oil, whether with dye or without, compared to the control plant without any treatment at all. So to summarize, we were able to obtain shellac nanoparticles for the first time in a very fast manner. These nanoparticles were able to stabilize an emulsion for up to 5 months with up to 40% oil. And these emulsions showed great potential as a crop signaling and sustainable marker for remote sensing. I would really like to thank my supervisor, our group members, Dr. Nana Kosman for the beautiful electron microscopy imaging, our collaborator, of course, the Kumanakis Institute, and you for listening. Thank you.